So first I'm going to do a quick explanation of recursive algorithms, and still in the context of Among Us, of course. So let's take a simple situation where you have one imposter and 4 crewmates, and you're at a meeting, right? After you vote, there's 2 options. Either you vote correctly, or you vote incorrectly. And, and so the amount of times that you vote correctly is, we'll just call it your win rate. And obviously when you don't win, you lose, so 1 minus. So if you vote correctly, then you win because you throw out the imposter. And so we'll just give this a number of +1, an EV of +1. And if you lose, well, then you have 1 imposter and 3 crewmates. And so this was the problem with just using a break even, is that what we win is very clear, we win the game. Our reward is very clear, we win the game. But the risk is not very clear because we don't lose a game, but we also don't win it yet. We just lost one of our crew. So when we're trying to calculate the EV of this in this scenario, it's not very clear what we should do with this. Because normally what we would do is just multiply the win rate by our reward and 1 minus the win rate by our risk. So what you do instead is you use a recursive algorithm, which just means in the algorithm, you call the algorithm back to it. So to find the EV of this branch, we'll call it, we find the EV of this branch using the same exact function. So that would look like this. So when we're at this branch, we, again, after we voted, there's 2 options. Either we vote correctly or we vote incorrectly. But this time, it's clear. If we vote correctly, again, we win. But if we vote incorrectly, there's only 2 crew left. So the imposter could just, kill one of them and we lose. And so for this branch, it is clear what the EV is. The EV is just the win rate times +1 and 1 minus the win rate times -1. And so with that, we can calculate the EV of this guy, and with the EV of this guy, we can calculate the EV of this guy. And so this is a simple example, but let's say you have, you're taking a more complicated example, such as with 2 imposters and 6 crew. In a case like this, obviously the tree will be bigger, but the mechanism is the same. It'll work through the tree until we get at these very clear scenarios. Which I will show later in the code exactly. And then once we find the very clear scenarios, we can work our way back through the tree to find the original EV that we were looking for. So that's a little bit on recursive algorithms. Alright, so the problem with this model that I drew up right here, which is in fact very simple, is that it's true, in this first branch everything makes sense. In this main branch, as I call it in the code, everything makes sense. But after we've voted a crew out, it's not that we immediately vote again and we get to choose another person to throw out and then we can calculate the EV. Instead, what happens is the game starts again. And so in this time, the imposter or imposters are able to kill, 0, 1, 2, maybe even 3 of the crew, which will change the possibilities for our EV. So our model has to take account for this and becomes a little more complicated. Alright, so this is the model with kills included in it. And so you see it did get a little bit more complicated, but it's nothing we can't handle. So again, we took the same situation with 1 imposter and 4 crew, except for this time after we vote incorrectly, so we don't win yet, the game doesn't end, we simulate the game. So you could see this, what's in this box right here is like the game. And so what I chose is for 1 imposter, there are 3 possibilities. Either 0 kills, so the crew doesn't change, or the imposter gets 1 kill, so the crew decreases by 1, or, and this happens less often, the 1 imposter gets 2 kills and the crew decreases by 2. So after the game has been played, again, only inside this box, then we get to voting. So obviously over here with 1 imposter and 3 crew, it's clear. If we vote correctly, we win. If we vote incorrectly, we lose, because we vote one of the crew out, and now we have less than or equal to twice the amount of imposters of crew. In this scenario, we have 1 imposter and 2 crew, so we're on 3 in total. If we vote correctly, we win. If we vote incorrectly, we lose. Again, it's very clear. What I did is I just set it so that if crew is equal to 1, then we lose as well. Because otherwise, the computer would see we have 0 imposters, and it would actually count this as a win. And so it would give this a positive EV of 1. In this case, we don't have that problem because crew is less than the amount of imposters, so we won't have that problem. The original point of this entire model is to find out what is the minimum win rate we need to throw somebody out given, an amount of imposters and crew. That's the goal of this model. But the problem is, we're looking for this win rate, and the problem is that we're assuming that win rate stays constant throughout the tree. So it doesn't exactly make sense in that regard. Because of that, there's also the ability to choose a win rate as if we were guessing. So in this case, it would be 1 out of 5. Over here, it would be 1 out of 4. Over here, it would be 1 out of 3, and so forth and so forth. And so in some ways, this guessing function is a lot more realistic because the certainty changes as we move through the tree, as it should. Because obviously, in a real match, players have less and less suspects throughout the game. And in that way, they usually are able to narrow it down to less and less people, and thus the certainty increases as the game goes through. Okay. And the other thing that I wanted to mention was that in the main branch, we do not factor kills. As you may notice, in all the other branches we do, after we vote, we simulate a game, quote unquote. But in the main branch, we do not do this because this is taken from the point of view that we have just played a game. So that's why we don't do this kill stuff in the main branch, but in all the other branches we do. Alright, let's head over to the code. We finally made it to the code, the function, the program, which gives us the minimum certainty that these last couple of videos have been about. So, the main function is this EV function. We also have this other one, which I'll explain in a second, but this one is the main function, as I said. So first of all, we define some stuff. And the one thing I'd like to draw attention to is this kills array, or list, I guess it's called in Python. And so what this is a list. As you see, 0 comes in twice. And the reason that I have that is because I didn't want to, the reason that I have that is because getting 1 kill for 1 imposter is more likely than getting 0 kills for 1 imposter or 2 kills for 1 imposter. And the same goes for 2 imposters. 2 imposters, I just assume that it's more likely that they get 2 kills than 3 or just 1. And the other nice thing about this array, or list, or whatever, is that we can just add the amount of imposters to get the kill array, the actual kill array. So you see -1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3. And that just makes it a little, nicer. Okay, so the first thing we check in this function is if we're at one of those end states. So if crew is less than twice the amount of imposters, so basically they can double kill or whatever, or crew is equal to 1. And so that's to check for that special case that I explained earlier. In that case, we return an EV of -1. And if the imposters are less than or equal to 0, then we return an EV of +1. So those are simple enough. So this here is just to add the possibility of guessing. If you don't give a certainty, we'll be guessing. And so the win rate will just be the imposters divided by the total amount of players. Okay, so here is where I make the distinction between being in the main branch or not. In the main branch, it's quite easy. What it does is it calculates the EV for if we vote correctly, and the EV if we vote incorrectly. And so that's just calling the same function again, but this time if we vote correctly with 1 less imposter, and if we vote incorrectly with 1 less crew. And so this will, trickle down until we get into these basic states, as I explained earlier. And so eventually, once it's found these EVs of the branches next to it, it'll return the EV of the correct times the win rate plus the EV of the wrong times 1 minus the win rate. So the definition of EV, basically. So if we're not in the main branch, what it's going to do, as you can read very nicely, is it's going to create a new branch for each possible kill that happens. So this is just a placeholder for all of the EVs of the branches. And so it's going to go through all of these kills in the array kills earlier. And so what it's going to do is it's going to, again, create an EV for a correct vote and an EV for a wrong vote. But this time, the EV of the correct vote, again, will have one less imposter. But this time, the crew will also have decreased by kill minus the amount of imposter. So in this way, it simulates, quote unquote, that a game has passed. And it does the same thing with wrong, except for this time, no imposters are thrown out and one extra crew is thrown out for voting incorrectly. And then it appends this EV with the exact same formula as over here. And then so what this will return is the average of all of the EVs of each kill. And so what I'd like you to notice is, like I said earlier, because these middle EVs come up more often, they will inadvertently have a higher weight than the outer EVs with those kills. And then this one is just a small little function to find the minimum certainty, because this one will just return the EV with a certain certainty, but this one will find the minimum certainty. But that's not that important. So let's get to some interesting numbers. First of all, I'd like to, using this model, answer the question, or the often stated statement of don't vote on 7. And so in a scenario of 7 players, you have 2 imposters and 5 crew. And so first I'm going to see what the EV is if we are guessing. And so that comes out to be a whopping negative 0.83. Remember that -1 is losing, so this is losing by a lot. So do not guess on 7, indeed. But let's just say that we are 50% certain that somebody is the imposter. Should we still vote? And so we still get a relatively relatively low EV, meaning that indeed we shouldn't vote on 7 unless we're a lot more than 50% certain. So that raises the question, how certain do we have to be to vote on 7? And it tells us that we have to be at least 63.7 or just 64% sure that somebody's the imposter to throw them out. And so this makes a lot more sense than the numbers that we got using a simple break-even calculation in the previous episode. So another interesting number that I found is, let's say that there are 2 imposters, right? 2 imposters, 8 crew. One of the crew dies, so now you have 7 crew, and somebody sees the killer kill him, right? So you call a meeting, you say I saw him kill or whatever, and that person gets thrown out. So there's 1 imposter left, and there is 1 less crew because they died. So in this case, we only need to be 20% sure that somebody is a killer to vote them out. So what this means is that in those, clutch videos that you see online, very, entertaining of course, but not realistic of optimum play, because as crew, you should definitely push for just randomly voting people out. And so this is one of those cases where because of how valuable the 1 last imposter is, and how not valuable the 7 crew are, it makes a lot of sense to push people out on the slightest of suspicions. And so now I'll just print out all of these numbers just so you guys have them. So here are all the minimum certainties that you have. So let's say you're playing in a random server with 1 imposter and 9 crew, and then you only have to be 15% sure that somebody is the imposter to vote them out. So let's say you just randomly saw somebody faking a task that they can't have or whatnot. you know, that's more than 15% sure certainty, I'd say. So you could just throw them out with a positive EV. You can ignore this infinity. That's just because you already lost with 2 crewmates and 2 imposters. And you can also ignore this 9 crewmates because that's not possible. But for the rest, oh, also you see here that 1 imposter with 2 crewmates has the exact same minimum certainty as 1 imposter with 3 crewmates. And that's because if you're in both scenarios, if you vote correctly, you win. And if you vote incorrectly, you lose. So this time we have the EVs instead of the minimum certainty, and we have the EV of voting randomly. So a couple interesting things is that the EV is negative everywhere. So it doesn't matter how many imposters there are, it doesn't matter how many crewmates there are. Turns out that if you vote randomly until you win or lose, it's always a bad idea. Areas where it's less of a bad idea is with 1 imposter and 9 crewmates. With 1 imposter and 8 crewmates, those areas. Some other interesting things is here with 1 imposter and 3 crewmates versus 1 imposter and 2 crewmates. Earlier, the minimum certainty was exactly the same, but here, the EV of guessing, so how bad or how good it is of guessing, is better when you have 2 crewmates than when you have 3 crewmates. And so this is pretty logical in that if you have 3 crewmates, then you know there's more crew than there are imposters. Whereas if you have 2, 1 out of the 3 times you're going to be guessing the right imposter. Other than that, most of the stuff makes a lot of sense. As in, your EV is really bad at low amounts of crew because the risk is very high. Alright, so that was the program. Thank you for watching.